Hello everyone, students. In the last lecture, you have learned about the linear combination of vectors in a vector space. Today, we shall develop one more concept, that is the linear span. It is also very much similar to that of linear combination, but there is a little difference which will be explained during the course of the lecture. So first you look at the definition of a linear span, then I will explain it through one example. So what is a linear span? If S is any non-empty set of a vector space VF, then the set of all the linear combination of any finite number of elements S is called the linear span of S. The linear span of S is denoted by Ls, and mathematically you can see that Ls is equal to summation I equal to 1 to n alpha I vi, such that vi belongs to S and alpha I belongs to F, and I varies from 1 to n. So students, look, what is linear span? Actually it is denoted by Ls, and it contains all the, actually it is also a set. It is also a set which is going to be a vector space again in the incoming lecture. But at present you can see that this set contains the element which are linear combination of elements of S. And this is the way how we write the linear combination of the given vectors. You can keep in your mind, for S is, when S is empty, then linear span of S contains only 0 element. Now I have taken one example to illustrate the above concept, that is the linear span. Today you will examine whether this capital Fx, which is in terms of polynomial, Fx is equal to 6x square minus 4x plus 1, belongs to the linear span of Fx is equal to x square minus x plus 1, and gx is equal to minus 3x square plus x plus 2. So here you are looking at three polynomials. One is capital Fx, another two are Fx and gx. In this example I am going to examine whether this Fx, capital Fx, can be placed in the set of linear span of small fx and gx. Whenever I talk about the linear span, it means I am talking about the linear combinations. So here linear span is of fx, small fx and small gx. So I will make the linear combination of fx and this gx. Then I will check whether this element belongs to this linear span or not. For that, what is the procedure? Look at here. If possible, let capital Fx is equal to 6x square minus 4x plus 1 belongs to the linear span of small fx and small gx. If it belongs to the linear span of these two items, then capital Fx can be written as the linear combination of small fx and small gx, with a and b belonging to the field which is here real number. Capital Fx is 6x square minus 4x plus 1, and small fx is x square minus x plus 1. Gx is equal to minus 3x square plus x plus 2. You make here little simplification, and after making a little bit simplification you will get these terms, this equation. And here you can compare the coefficients. The coefficient of x square is 3a minus 3p in the right hand side, and the coefficient of x square is 6 in the right hand side. So these two terms can be compared and equated. Similarly, when you compare the coefficient of x, you will get minus a plus b is equal to minus 4. And the constant term is a plus 2b here, and here the constant term is 1. Now you have three equations, 1, 2 and 3. From the first two equation, when you solve these two term equation, you just add these two equations, you will get the value of b as minus 1, and when you will put the value of b as minus 1 in one of the equation, you will get the value of a as 3. So from first and second you got the value of A as 3 and B as -1. When you substitute these two values in the third equation, this will get satisfied. It means I can write fx, capital Fx, as a linear combination of small fx and small gx with scalars 3 and -1. Hence, this capital Fx belongs to the linear span of small fx and small gx. This is how we check the linear span of the given elements. For your practice, I have given you two questions, problem number 18 and problem number 19. You can prove these. Problem number 19 is nothing but a theorem, and problem number 18 is some numerical problem, and you have to solve these two problems by yourself. Thank you.